Structural aspects of a parameterized complexity. Part 3 of this book is concerned with various structural issues concerning the parameterized complexity framework. In general, these are much harder to resolve than the analogous questions concerning classical complexity classes and the degree structure of polynomial time reducibility. One of the results presented in Part 3 provides an explanation of the difficulty of the subject, whereas ordinary polynomial time reducibilities are sigma 2 to the 0 in a arithmetical complexity, parameterized reducibility, yield index sets that are sigma 4 to the 0 complete. There are several kinds of structural questions that are explored in Part 3 and elsewhere. What is the evidence that the WT hierarchy is proper? What are the relationships between classical and parameterized complexity issues? What are the connections between parameterized complexity and approximation complexity for the optimization problems? To what extent do analogs of classical theorems hold for a parameterized complexity? For example, could it be that W1 net equals to FPT, whereas for OT, which is greater than or equals to 1, WT equals to W1? This is entirely compatible with P not equals to MP. One of the results presented in Part 3 gives a computational basis for the WT classes based on uniform parameterized circuit families of depth T and establishes that these circuit families underlying the WT hierarchy form a proper hierarchy of a non-deterministic computational power. Another result shows that the implication FPT equals to W1 implies P equals to MP cannot be proved by any argument that relativizes. Despite this evidence that the conjecture that the W hierarchy is proper is strictly stronger than the conjecture that P not equals to MP, there is still some connection between the two frameworks. If FPT equals to W1, then it is possible to solve classical 3 set in time 2 to the little o of n for expressions having n variables. The complexity of the reductions mean that simple delayed diagonalization arguments from classical complexity theory need to be replaced if they hold at all by complex priority arguments. For instance, a relatively deep result presented in Part 3 is a partial analog of Leitner's density theorem. Many possible analogs of classical structural theorems remain open. It is unclear to what extent structural complexity theory, as we know it classically, can follow Cook's theorem into parametric miniaturization.